friends, as I told in the previous video, we'll be looking into some of the applications of this Euclid division lemma for positive integers. So here is one of the question. Show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1 where q is some integer. So this we are going to prove that every positive even integer. So we are going to consider only the positive integers, and here the even integer we have to show that it is in the form of 2q, and the odd integer we have to show that it is in the form of 2q plus 1. So for this, let us proceed by assuming that let a be any positive integer. So let a be any positive integer. So if I have taken a to be a positive integer, so here b becomes 2. Why I have taken 2 here is because we have to show that it is of the form 2q and 2q plus 1. So b becomes equal to 2. So this implies b is equal to 2. So according to Euclid division lemma, if there exist two integers a and b, then there also exist integers satisfying a, q and r, satisfying a is equal to bq plus r. So here a is any positive integer and b is equal to 2. So I can write this as, according to Euclid division lemma, a is equal to 2q plus r, where b is equal to 2. If b is equal to 2, so here if b is equal to 2, we know that r's value should be only either equal to 0 or it should be less than b. So what are the values which r can take? If b is equal to 2, r will be equal to 0 and 1. R can be equal to 0 and 1. And therefore, I can write a is equal to 2q or a is equal to 2q plus 1. Now let us look into these two probables. A is equal to 2q and a is equal to 2q plus 1. Now clearly it is seen that if a is equal to 2q, it is divisible by 2 and therefore it is an even integer. And a is equal to 2q plus 1. So any even integer, if you add 1, it becomes an odd integer. So here we can clearly say that for any positive integer is of the form 2q or 2q plus 1. So here 2q is divisible by 2. So this implies a is equal to 2q is even integer. And similarly here 2q plus 1 is not divisible by 2 and therefore a is equal to 2q plus 1 is an odd integer. So here we have proved that for every positive even integer it is of the form 2q and for every positive odd integer is of the form 2q plus 1. So now we shall deal into another question which says that use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So let us look at the question and understand it better. So we are going to see that we have to show that square of any positive integer is either of the form 3m or 3m plus 1. So for this, again the same procedure. Let us consider a to be a positive integer. So let a be any positive integer. So here if we are taking it as a as a positive integer, then what can be the possibility of b being So b here is equal to 3. So b is equal to 3. Now applying Euclid's division lemma, EDL. So what we get, A is equal to 3q plus r. 3q plus r. So here what can be r? So r can be equal to 0, 1 or 2 because r should be less than b. So here A is equal to 3q plus r and therefore here B is 3, therefore r should be necessarily 0, 1 or 2. So when r is equal to 0, A is equal to 3q. If A is equal to 3q, but we are going to find the square. So this implies A square is equal to 3q the whole square. So that is equal to 9q square. And you can write this as 9q square as 3 into 3q square. That is equal to 3m. A square is equal to 3m. So next, when r is equal to 1, A is equal to 3q plus 1. But we are going to see the square here. Therefore, A square is equal to 3q plus 1 the whole square. So that is equal to 3q square is 9q square plus 6q plus 1, and this I can write it as 3 into 3q square plus 2q plus 1, that is equal to 3m plus 1. So here in both the cases where m is equal to here 3q square and here m is equal to 3q square plus 2q. So what? We are going to apply the same thing when r is equal to 2. So here you have A is equal to 3q plus 2, but we are going to find out the square. So A square is equal to 3q plus 2 the whole square. So that implies A square is 9q square plus 3 to 6, 6 to 12 q plus 4, and this I can write it as 3 into 3q square plus 4q plus 1 and plus 1 here. 3 into 1 is 3 and plus 1 becomes 4. So this is nothing but 3m plus 1. So again here we got A square is equal to 3m plus 1, where m is equal to here in this case 3 square plus q square plus 4q plus 1. So here we have proved that by applying this Euclid division lemma, we have showed that square of any positive integer is of the form 3m or 3m plus 1. So again here we have taken A to be any positive integer, b is equal to 3, therefore r becomes equal to 0, 1 or 2. So the positive integers we can write it as A is equal to 3q or A is equal to 3q plus 1 and A is equal to 3q plus 2. But we are going to see the square of these positive integers, so we have taken squares here and we have proved that A square is equal to 3m or 3m plus 1. In both the cases you get 3m plus 1. So this is one of the beautiful applications of Euclid division lemma.